guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. Now we move on to talking about reaction mechanisms, which is the number of steps it has to take to form the product. And so the rate of reaction depends on the reaction mechanism. So as an example, let's look at NO2 plus carbon monoxide going to NO plus carbon dioxide. And the experimentally determined rate law was rate equals K NO2 squared. So this 2 tells me that this is an order of 2 with relation to the concentration of the NO2, which is a reactant. So what's the reaction mechanism? Well, we know that the rate is proportional to NO2 squared. So the reaction most likely involves 2 NO2 molecules colliding to form either the product or an intermediate. And since 2 NO2s cannot form NO and CO2 since there's no carbon involved, there must be an intermediate species. And so from here we can propose an intermediate species. Let's say NO3, which is not a reactant and it's not a product since it's an intermediate species. And so the proposed reaction mechanism from here has 2 steps. Step 1, NO2 plus NO2. Like we said before, since it's an order of 2, it most likely involves 2 NO2 molecules colliding together in the first step. And this forms NO3 plus NO. And this is given the rate constant K1. And then step 2 would involve the intermediate NO3 colliding with carbon monoxide to get NO2 plus CO2. So looking at these 2 steps, the overall reaction is going to be NO2 plus CO going to NO plus CO2. The reason being that the intermediate species can get canceled out since they're on either side. And this guy can also get canceled out. So the initial NO2 that collided can also get canceled out with the one that was formed in step 2. And so the 2 things you really want to consider when looking at mechanisms is that the sum of the elementary steps equals the overall reactions. And so this is the overall reaction, which is what we wanted, and it's a sum of all of the individual steps. Secondly, the mechanism must agree with experimentally determined rate laws. And so in this case, we determined that the rate equals K NO2 to the order of 2, and that's why we had to take into consideration colliding 2 NO2s in one of the steps. And so from here, we want to determine what the rate determining step is, and this is a very important concept. So the rate determining step is the slowest step in the reaction, and it has to be the one that is directly related to the overall rate. And so the mechanism has to be based off of the rate determining step. And in this case, the rate has to be proportional to the concentration of NO2 squared, which means that step 1 has to be the rate determining step because that's where the 2 NO2 molecules are colliding. So that's the slow step, and that's the one that determines the overall reaction rate. And so the rate is equal to K1 NO2 squared due to the fact that step 1 is the slowest step. And so this proposed reaction mechanism agrees with all the different things that we talked about that has to be taken into consideration when proposing a possible mechanism. And so this does not necessarily prove that a reaction mechanism is correct, but it does show that it is highly possible. So now I wanted to show you how the elementary step is related to molecularity and thus the rate law. And so molecularity is the number of species in an elementary step. And so, for example, bimolecular is the collision of two species, whereas unimolecular only has one species. And so the rate law for each elementary step follows directly from the molecularity. And the overall rate law is the rate law of the slowest step, like we talked about before with the rate determining step. And so if the elementary step is A going to B, this is unimolecular because it's just one species. And the rate law is just Ka, so an order of 1. But now if we had A plus A going to some kind of product, let's say B, or this can also be 2A going to B, now this is called bimolecular. And the rate is written as Ka squared with an order of 2. So things can have also bimolecular molecularity and have two different species that are colliding. So let's do A plus B going to C. This is again bimolecular, but the rate law is going to be Ka, A, and B. But since the individual rate order for A is 1 and for B it's 1, the overall order is going to be 2, just like the one before. And so now what happens when you have two of the same species, but then a third different guy? And this goes to C. And this can also be written as 2A plus B going to C. Now this is called termolecular, which you don't see very often, but it's good to know. And the rate is written as Ka squared, since you have two A's colliding, and B. And so since the order of A is 2, the order of B is 1, the overall order is 3. Final example, if you have A plus B plus C going to D, then again this is also termolecular, and the rate is going to be dependent on each individual concentration. So A, B, and C, each individual order is 1, and the sum is going to be 3. And so the probability of 3 molecules colliding simultaneously is very unlikely, so that's why termolecular reactions are much less common. And that's why, for the most part, we focus on the unimolecular and bimolecular reactions. So one thing that students often confuse is the difference and the relationship between little k and big K. So this little k represents the rate constants that we've been talking about in this topic, and the big K represents equilibrium constants from a previous topic. So the ratio of rate constants is equal to the equilibrium constant, and we can show this by the following analysis. So let's say A plus B goes to C plus D, and the equilibrium constant, big K, is the concentration of the products over reactants, if you remember doing this. And so let's assume this reaction is an elementary second order reaction. And so that means that A plus B goes to C plus D, and the forward rate is equal to K AB. And remember, this is little k, although it's hard to show that this is little and this is big. This is the rate constant. And then if you have C plus D going to A plus B, this is the reverse rate, which is often given this little comma above the K. And this is C, D. And so at equilibrium, the definition of equilibrium is that the forward rate is equal to the reverse rate, right? And so that means K AB is going to equal K reverse C D. And so we can rearrange this so that it looks like the equilibrium constant equation, where K over K is the concentration of the products over the concentration of the reactants, which is equal to big K, or the equilibrium constant. And we can now see in kinetic terms rather than thermodynamic terms when to expect a large equilibrium constant, where, for example, K is greater than 1 when products are favored, when the little k for the forward reaction is much larger than the K prime for the reverse direction. So K is much greater than the reverse. And so now we can see the relationship between the rate constant and equilibrium constant, and I hope that you won't mix them up because that's a really important thing to keep separate for this topic.